Distinguished colleagues and guests, good afternoon. It's November 18th, 2021, 3 p.m. Moscow time. First of all, I believe members of the board have already done it, and others are also turning off the sound on the mobile phones. We're beginning the panel session for the defense of the thesis by Vladimir Prokofev. The thesis is submitted for the academic degree of candidate of sciences in physics and mathematics. The specialization is semiconductor physics. The topic of the thesis is luminescence of multilayer dielectric structures on silicone surface. Under the order issued by the academic secretary of St. Petersburg State University as of September the 1st, 2021, I, Oleg Vavenko, Doctor of Sciences in Physics and Mathematics, Professor of the Department of Solid-State Electronics at Petersburg State University, was appointed the chairman of the board. The order also approved the members of the board, namely Maria Zamoranskaya, Doctor of Sciences in Physics and Mathematics, a leading researcher and the head of the diffusion and defect formation of semiconductors laboratory of the Alpha Physical Technical Institute of the Russian Academy of Sciences. Alexei Kamalov, Doctor of Sciences in Physics and Mathematics, Associate Professor of the Department of Solid-State Electronics of St. Petersburg State University. These are the colleagues who are present here in the room. And the following members of the board are working remotely today, namely Denis Vyalokh, Doctor of Sciences in Physics and Mathematics, Professor of the Donostia International Physics Center from Spain. Do you hear us and see us? Yes? Okay. And Adil Abdul-Melikovich Yefyasov, Doctor of Sciences in Physics and Mathematics, Associate Professor of the Department of Solid-State Electronics in Petersburg State University. And our candidate for the degree is Vladimir Prokofev. Also, we have the thesis supervisor, Alexander Baraban, Doctor of Sciences in Physics and Mathematics, Professor of the Department of Solid-State Electronics of St. Petersburg State University. And I would like to inform you that the panel session of the dissertation board is being recorded and broadcast on the St. Petersburg State University website, and it is also interpreted from Russian into English and vice versa. I would like to inform you that currently we have an email address posted on the page with live broadcast of the board session, and all the listeners can submit their questions to Mr. Prokofev online. The questions regarding the thesis or scientific discussion, and the listeners can also submit their opinions, and thus they can participate in the scientific discussion. And these questions will be forwarded to me by our technical service, and I will read them out during the discussion. The questions must be related to the speech of the candidate and to the content of the thesis, and do not forget to give your name, position, and position if you submit a question. The questions that have nothing to do with the scientific discussion, with the text of the thesis, and anonymous questions will not be voiced. Under the order on the procedure of granting academic degrees at St. Petersburg State University, approved by local normative acts, the session of the dissertation board is valid, providing 2/3 of the appointed board members are present. The total number is not to be fewer than 4 people. Our dissertation board consists of 5 people, and everyone is with us today, including 2 members of the board who are working remotely. And we have a multimedia connection with them, therefore we have a quorum. And I kindly ask the member of the Department of Dissertation Board Support to fill out the attendance list. And our session should not last more than 2 hours. And the agenda is as follows. First comes the chairman's presentation about the documents submitted by the candidate for the degree and their conformity with the requirements, the chairman's replies to questions, if any, followed by the candidate's presentation, providing an overview and findings of the research, then questions to the candidate regarding the presentation, 2 minutes for the candidate's replies to the questions, the reports on the thesis. The board members will be taking the floor in turns to provide their reviews and questions on the thesis. 10 minutes each. Then the chairman's report on the thesis, also 10 minutes for that. Then the candidates' comments about their reports on the thesis and replies to the questions. Then open discussion, the speeches of those present at the defense with a brief presentation of their positions or questions or suggestions to the candidate on the topic of the research. No more than 2 minutes per person. And don't forget to state your full name, academic rank, position, and place of work in the registration list. Though we don't have such guests today. Then, the chairman will ask the questions submitted during the broadcast via our website. And those who are listening and watching us online today, I would like to draw your attention to the fact that written questions, that the reading of which will take more than 2 minutes, will not be voiced. Then the candidate's replies to the questions, 2 minutes for that. Then the presentation of the candidate's thesis supervisor. Then the candidate's closing speech. And after that, we may have 5-minute closed discussion and open balloting, and then we're going to make a decision on whether to confer the academic degree or not. Any questions about the agenda? No objections? Okay, none? Okay. Thank you then, and let me proceed. So, first of all, a few words about Vladimir Prokofev. His thesis, well, I won't repeat myself. So the thesis was approved for the defense by the order of the Academic Secretary of St. Petersburg State University as of August 16, 2021. Vladimir Prokofev has prepared his thesis at St. Petersburg State University as a postgraduate student, and Alexander Baraban, Doctor of Sciences in Physics and Mathematics, Professor of the Department of Solid-State Electronics of St. Petersburg State University, is the thesis supervisor. 9 published works describe the research findings, and they include 4 papers published in peer-reviewed journals recommended by the Ministry of Education and Science, and 5 papers in publications indexed in Web of Science and Scopus. And all the documents provided by the candidate for the degree, as far as I'm informed, are in compliance with requirements of St. Petersburg State University, and they are kept in the certification file of the candidate for the degree, and the curator of the defense, member of the Department of Dissertation Board Support, has all the copies of these documents. That's Natalia Vladimirovna Karpova. And before I give the floor to the candidate for the degree, I have a question to all the members of the board. Do you have any general questions to the candidate for the degree, and is there need to consider the whole list of documents submitted for the defense? No questions about that. Okay. So, Vladimir, please, you have the floor. So that's the topic of my report, that's the topic of my thesis. And currently, the structure with silicon dioxide are the basis in hard-body electronics. And currently, there's a lot of interest to tantalum pentoxide. And it is interested by the due to its excluded zone and due to its permeability luminescent methods for the diagnosis of silicone dielectric arise interest not just because they are informative, but also because they provide an opportunity to obtain electronic construction of the solid body. And currently, we know that thermal silicon dioxide consists of such chains closed in rings, and the main structure here is a tetrahedron CO4. And some violations in the neighboring tetrahedrons will define the major defects. And here we consider the defects of silicon dioxide and the defects that we find after the formation. And here we know about 4 centers, the ones that are given here on the slide, with mono vacancy, oxygen vacancies. And if we talk about the optic characteristics of defect, the majority of authors say that for the band of 9.8 electron volt, for this band oxygen is responsible, and for other bands the oxygen deficit is responsible. Tantalum pentoxide can be got in crystallic and amorphous phases, and the width of the excluded zone is as follows: 4.5 electron volt. Tantalum pentoxide has a broad spectrum that many authors observe in different types of luminescence, and most authors believe that they are associated with oxygen deficit centers. And overall, we can say that the nature of luminescence centers and so for thermal silicon dioxide, we've chosen 4 widths, and we carried out electric, photo, and cathode luminescence. Here, tantalum pentoxide samples were received on this installation, and the main achievement here is that we got it from solid phase, and we worked on the substrate as well. We deposited on the substrate, and we managed to grow thick layers during a short period of time. And here, these pictures show the cuts of tantalum pentoxide. We've chosen the growth conditions, the temperature of reagent, the temperature of substrate, the speed of rotation of the substrate, and thus we got rather stable and accurate samples. And on the pictures, you see the difference between the phases. And the spectrum of electroluminescence was received on our software complex based on monochrometer. And the registry part was developed by us as well, and we changed it a bit, changed the drive of the mesh, and due to that, in the automatic regime, we got the spectra of electroluminescence. And at that, the installation allowed us to work in the scanning regime. We could rotate the mesh at once and got spectra. And we needed it in order to reduce the time and reduce the field impact on the sample. Thus, we managed to obtain spectra for tantalum pentoxide that easily degrade in the field. Cathodoluminescence spectra were received at St. Petersburg State University Resource Center. And when we get cathodoluminescence, we can measure the energy of the primary beam. And here you see the computation of electron loss in samples. To the left, that's a thick silicon dioxide, and to the right, that's tantalum pentoxide. And changing the energy, we can see that we can change the depth of emergence of luminescence. Photoluminescence was observed on the installation that consists of 2 different monochrometers, and it allowed us to get the spectrum that is normalized by the energy of excitation and the apparatus function of monochrometers. And we used voltmeter verification devices, and the installation allowed us to get high-frequency CV characteristics and get external shift. And it also allowed to automatically implement the method of field cycles. So we got the cathode luminescence spectra for for silicon dioxide, depending on the thickness, and we got the spectrum split. And as a result, we can see that our whole set of spectra can be divided into a unified layer of bands that is approximated with different intensities of the bands. And we got the spectral for electroluminescence depending on the thickness and depending on the current. We got the split for the spectrum, and we can see that there is a whole set of bands to which we can divide the spectrum. And we got the decomposition of the spectrum for photoluminescence, for silicon dioxide. And photoluminescence is interesting here because for cathode luminescence and electron luminescence, with the growth of thickness, we've seen an integral growth of spectral intensity. Here, the picture is completely different. Up until 123 nanometers, we see the drop of intensity, and after that, at 124 nanometers, we see drastic growth and the change of spectral band content. And we got the excitation spectra for luminescence, and we carried out approximations of spectra, photoluminescence, and excitation of photoluminescence. And if we compare electric and cathode luminescence, it turns out that we can choose the whole set of bands and divide it into groups, and there is one exception that was not detected for cathode luminescence. And in this spectra, the main difference is in band 2.2 electron volt. That's the brightest band for cathode luminescence, and for electronic luminescence, it's not that bright. And that's the obvious example of what I've already mentioned. Cathode luminescence and electron luminescence, and you see the difference in 2.2 electron volts, and to the right you see this violet zone. And overall, it turns out that for cathode and electroluminescence, we have three major bands, the brightest ones that we would like to dwell upon: 1.9, 2.2, and 4.2. In order to get information about these centers, we carried out a series of studies. In the first case, we conducted the study for cathode luminescence, measuring the energy of the beam, and thus we managed to get information from different layers on the thickness. Next experiment was conducted for the etching of the samples, and we compared the intensity of spectra on one width, but one of them was received directly, and another sample was grown up until higher thickness. Then we used etching to reduce the thickness. And above all, we got the spectra depending on the intensity of the bands of luminescence, on the thickness of the dielectric layer. And as a result, if we consider the results of the study for structures of silicon dioxide, first of all, photoluminescence does not have another spectrum, and we don't see the development of the same bands as in cathode luminescence. And as for the bands, we can say that for 4.2 electron volt, the centers of luminescence are scattered across the volume, and their concentration depends on the time of oxidation. And 4.2 band is the only band that is not dependent on temperature. And for the band 2.2 electron volt, we had it that the center of luminescence has even concentration across the width, and a number of luminescence centers is proportional to the thickness. And for 1.9 electron volt, we knew that it's localized in subsuperficial area, and currently we believe that its intensity is defined by non-binding oxygen. And if it's so, then we ought to expect maximum intensity of this band in those samples that were obtained by dry oxidation, because hydrogen and its derivatives can transfer non-binding oxygen into selenol groups, and that's true for photoluminescence. And as for cathode luminescence, we got it that the intensity of bands is high in samples with high number of selenol groups. Thus, we offer the model of the band formation for 1.9 electron volt for silicon dioxide that is associated with selenol groups, and this was confirmed experimentally on samples in which field degradation was reduced the number of selenol groups artificially. And now let's consider the tantalum pentoxide samples. We got the cathode luminescence spectrum of our samples on silicon, and we got the split of the graphs. And we got a cathode luminescence spectra for multilayered samples, and we carried out the split. And for multilayer structures, we see that the spectrum contains elements of each of the layers. And we carried out the tests of structures in electron luminescence. We considered multilayered structures, and we got the split as well. And in case of electron luminescence, the general spectrum of the multilayered structure repeats the structure of each of the layers. And we got photoluminescence spectrum for tantalum pentoxides, for multilayered structures, and for tantalum pentoxide. We got photoluminescence and excitation photoluminescence structures, and as for photoluminescence, it turned out that the spectrum of photoluminescence structures on silicon coincide with photoluminescence of tantalum pentoxide on silicon oxide. So photoluminescence does not see this layer of tantalum pentoxide. And as a result, if we talk about general luminescence structure with tantalum pentoxide, it can be said that in case of tantalum pentoxide, we managed to select the set of bands that gives us cathode, electron, and photoluminescence. And we also got the coefficient of permeability for tantalum pentoxide, and based on the comparison, the permeability coefficient was connected to the processes that happen in tantalum pentoxide in the excluded zone. And based on that, we offered the model for electronic position of tantalum pentoxide. We believe that in the excluded zone, we see the set of layers and the transition from which is observed in luminescence. And it's not important how electrons emerge there in the conductivity zone. It may be photoluminescence or injection of electrons in case of electron luminescence, but still we see the same bands in all three cases. We also offer the model of spectrum formation, and the main peculiarity here is that when we apply tantalum pentoxide on silicon dioxide, there is a drop of intensity of 1.9 electron volt band that is quite vivid for tantalum pentoxide, and we see an additional band that is localized at interface border of two dielectrics. And thus, the conclusions are as follows. We obtained samples with tantalum pentoxide on the developed unit. We carried out their studies using luminescence methods. In order to study electric luminescence, we've developed an installation that allowed us to obtain the centers of luminescence, and for silicon dioxide, we've carried out an analysis of the spectra, and the major bands 1.9, 2.2, and 4.2 electron volts were obtained, and it allowed us to improve the understanding of these bands. And we also offered the model of electron construction of tantalum pentoxide, and we offered the model of photoluminescence construction in multi-layer structure. That's it. Thank you. So please, questions? First of all, the members of the board.
Да, вопросы именно по докладу,
Yes, the questions on the report, because those questions that will be that we've written in the reviews will be voiced afterwards. Well, I have a slide with provisions for the defense and the conclusions that I've given. They actually are just the same as the provisions that were offered for the defense. Other questions? Okay, then I have several. The first question that was voiced that you got certain samples at with different widths. How did you define? How did you choose this width? We tried to take. Well, first of all, we were focused on the presence of these samples, and they were evenly distributed across the thickness. And third is that those were high-quality samples that we had. We had numerous samples, therefore we could use them freely everywhere. So you grew them at different widths, yes, and you've chosen some of them. Do I get it right? Yes, for tantalum pentoxide, we've grew a lot of samples, but due to the difficult electronic structures, we've chosen the widths that would allow us to say something at least. So we've chosen tantalum pentoxide thickness that is equal to double thickness of silicon dioxide, because the field is higher for silicon dioxide, so that according to our requirements we could carry out the measurements so that we would understand how the fields are distributed, and we used electroluminescence mostly. So you are saying that these thicknesses were chosen according to the best suitable parameters for this study method, yes? Okay. So how long did the cycle take? The full measurement, the full sample acquisition cycle took us 5 minutes. So it turns out that one cycle took a quarter of the second. That's really a great result, because the typical speed is 3 orders lower. So it's surprising how you could secure that. Now, show us the 8th slide, please. Over here. I think is that this cut is seen quite well. And what's that on the wall? Is it dust? What is it? I believe that's just uneven structure, but depending on the temperature of the reagent, we could get samples that were not that even, and at a temperature more than 85 degrees on the surface of the film we had certain growths. And it's likely that it's either the violation of the cycle, local cycle, ALD cycles. So we believe that's tantalum pentoxide that grew so unevenly. Okay. And last question. You didn't see this band of 4.6 in luminescence. Do you have an idea why you didn't see it? Is that an effect, or maybe that's due to the equipment that you use? Did you choose this did you check this results of computing? We carried out a lot of cathode luminescence studies, and as for this band specifically, I'm not sure. It's hard to answer right now. Okay, thank you. No one else wanted to ask questions. Okay. Now, as there are no other questions, let's listen to the members of the board and to their reviews. And I offer to answer the questions after every review. So, do you support this idea? Yes, okay. And second point is that basically all the reviews were already published on the website and everyone could read them out. Therefore, there's no need to read all these reviews. You'd rather choose the key points with criticisms and remarks. And first of all, I would like to give the floor to Денис Вялых. So do you hear me? Yes? Yes, we do. Yes, we do. Okay, thank you so much. I would like to thank you for the invitation and for the opportunity to read this thesis and to participate in the work of the board. Overall, I had a very good impression of this work. It is really well prepared, and it's obvious that the candidates spent a lot of time on testing everything, and I really appreciated it. The work is quite logic, and it's well written both in English and in Russian. The English version is also quite clear-cut. It's easy to understand. And I also considered the works that were published. Really good articles, quite clear, and I believe that they will be rather popular among the experts. And I had several questions that I've given in the end of my review, but actually answers were already provided during the presentation. But I have, well, two questions left, the third and the fourth in my review. So what's the nature of the centers of luminescence that are responsible for the bands of luminescence in 1.9, 2.2, and 4.2 electron volts? And the second question, why, in case of structures of silicon dioxide, spectra of photoluminescence are different from the spectra of cathode and electroluminescence, and in case of silicon tantalum pentoxide, this spectra nearly coincide. So the answer, well, according to many authors, for photoluminescence, this band of 1.9 electron volt is explained by non-bridging oxygen. We agree with them. And as for the rising of luminescence by electrons, we proposed a model of the band, and we believe that it is associated with the presence of selenol groups in the sample, and selenol groups collapse, degrade, and we have a defect of excited state, and for bands of 2.2 and 4.2 electron volts, I can give just my opinion. I don't have exact proof for the nature of such centers, but basically the structure of 4.2 electron volts allows us to think that it is associated with excessive oxygen that emerges, and for 2.2 electron volts we presume that it was an even vacancy of oxygen. So it turns out that no matter how long you grow the oxide, and no matter where you took it, you have some part of defects. And that's it. Like when we build a brick wall, every 10th brick is emitted, and for 2.2 electron volt, I believe that's something like that here. And as for the differences in luminescence for tantalum pentoxide and silicon dioxide, we can't say it exactly, but we believe that our ideas are based on some peculiarities. First, we believe that for silicon dioxide we have intercentral luminescence, and for tantalum pentoxide we believe that there is a set of bands in the excluded zone. And above all, for photoluminescence, our installation just lacked excitation in order to for electrons to reach the conductivity zone for silicon dioxide, because excluded zone is 8 electron volts, and for us the radiation was lower. And for tantalum pentoxide, all the three luminescences could push the electrons to the conductivity zone. Therefore, we believe that it is maybe associated with that. Denis, are you satisfied with the answers? Yes? Yes, I am. I wanted to ask, how do you see the development of this instrument that you've used for the measurements? How do you think how will this instrument develop, and will it be developed by PhD students, by the further generations? Well, I believe that's quite an interesting result that we managed to obtain. We carried out 3 studies for cathode electric and photoluminescence, and you see, I expected that when I finish, you'll ask me what luminescence is better used, and I'll say you'd better use this method. But essentially, it turns out that every method has its own peculiarity that makes it better to use in some other cases. Therefore, I believe the result was quite interesting. Yes, the only thing that I want to ask you to read is your conclusion. Yes, the conclusion is as follows. That's a very good work. It is well structured, and it has quite obvious novelty, and its practical value is obvious. All the provisions are accurate and well worded, and I have a very well impression of the thesis overall. Okay, thank you. Now, I would like to give the floor to Maria Zamarianskaya. So, for me, this work was quite fascinating because I worked with cathode luminescence of CO2. Those results that Vladimir obtained with 3 modes of excitation of thin films that allowed to study the distribution of these centers of luminescence and defects across the depth. They are quite fascinating, and regardless of the fact that this material has been studied for a long period of time, still there are new opportunities that are found all the time, because we still lack answers to some of the questions. But still, all the results are quite interesting, and they are novel. The opportunity to use 3 ways to excite this luminescence opens up new opportunities that can't be otherwise secured. And we can see from this work that the candidate for the degree invested a lot of efforts to develop the methodologies and the technologies of growing films. That's the combination of working with your hands and head, and quite interesting conclusions. Therefore, this work is really good, and it deserves a very high mark. But still, I had a range of comments, and I'll read them out. In the work, you provided the studies of the spectra of excitation for samples, but for photoluminescence, yes. And however, I have not seen this conclusions about these results that could be obtained. And when you split this luminescence spectra, you give a lot of bands, and in the thesis you mention the interpretation of 3 of them, and it's not clear why you had to give such a split with such an accuracy. So is it really essential? And in the work you give the spectrum of radiation of the silicone substrate with a maximum of radiation of 500-600 nanometers. And silicone without silicon dioxide has such luminescence. And this result is quite interesting, but it is not discussed in the work. Therefore, it would be nice to hear what you think about it. And in chapter dedicated to the study of cathode luminescence, you say that luminescence spectra are normalized at the energy of primary electron beam. I did not understand what you're referring to. But overall, the work creates a very good impression, and certainly Vladimir deserves the academic degree of the candidate of sciences in physics and mathematics. Okay, Vladimir, you can answer. Yes, thank you for the review. And let me start from the end. As for normalizing, indeed, it's the incorrect choice of wording. This normalizing was used in one of the experiments. And essentially, what we did, we drew the dissipation graphs of electrons across the width of the sample, and we compared. And normalizing was done when integral was 1, and we used it during the experiment when we had an experiment with silicon dioxide, and we changed energy and arose this same number of excitation centers, so we tried to carry out the depth profiling. And as for excitation spectra of photoluminescence, we were used in order to obtain the electron structure of tantalum pentoxide, but they were just not described in the work. And as for the number of bands in the spectrum, you see, we got them, and in our work we discussed the key bands that were obvious, but still it helped us for tantalum pentoxide when we had the comparison of 2 spectra of cathode and electroluminescence that gave us the bands that we used in the split. And as for silicone, we can't say anything particular about it, because the aim of the graph was to understand whether it helps or not, whether it adds up some distortions or not. And therefore, when I obtained this graph, we understood that there are no deviations here. That's how we used it. So, yes, that's luminescence, and that's a valuable result. As such, okay, no and no, okay. So I'm satisfied with the answers, okay. So, Adil Yefasov. So do you hear me? Do you hear me? Yes. Yes, we do. Okay, great. Well, I liked the work, indeed, because there are 3 types of luminescence on the same samples, and that's always interesting to have a look at such a comparison done. The work is quite accurately written, but still I have certain comments, that not methodological ones, but still. You have a lot of measurements in the system of semiconductor electrolyte, but you don't give the type of electrolyte, and you don't give the pH of the solution in the text of the thesis. That's the first question. The second question, on page 65, the barrier of silicon dioxide equals 4.2 electron volt. Where did you take this figure? It's either measured by you or you need to give a reference. Similar question for page 78. You give the width of the value of the barrier, 1.33 electron volt for the system of tantalum pentoxide electrolyte. Where did you take this figure? Either a reference or an explanation should be given here. Then you measured CV characteristics, and you could somehow assess the density of quick superficial states. Did you do it or not? Or maybe slow superficial states. And the last question, you say that you have such a phrase here, injection of electrons from electrolyte according to Fowler Nordgame mechanism. Is it your own idea? If you measure volt-ampere characteristics, you do it for several orders, and I haven't seen these pictures, or that's not your result, and in this case you should give a reference as well. But overall, I liked the work a lot. Therefore, I believe that Mr. Prokofev deserves the academic degree of the candidate of sciences in physics and mathematics. And I wish you success. Thank you. Okay, Vladimir, please. Yes, thank you so much. As for the electrolyte, we used sodium to SO2. Sodium to SO4, I believe. You misspelled it, yes. And as for barriers, the barrier between electrolyte and silicon dioxide was obtained in our lab previously. And we have literature that was, I just omitted the references in this place. And as for the barrier between electrolyte and tantalum pentoxide, it was assessed by the relation of electron we need for our electrolyte, and it was measured before in our lab. And as for tantalum pentoxide, that's literature data. And as for Fowler Nordgame, indeed there are works that were conducted by our lab previously that CV characteristics are found here for silicon dioxide. So they are even in the coordinates of Fowler Nordgame. Yes, the density of quick superficial states. We did not assess this density. We used CV characteristics to get the sum effective charge, and we used it in the field cycle method. Okay. Okay, the last question, just to specify. Did you measure the potential in a semiconductor electrolyte? What electrons did you use? Platinum electrons. Thank you. Yes, I'm satisfied with the answers. Okay, thank you. So, Alexei, the floor is yours. Here's the microphone. Well, as for the relevance, I would mention that there are appropriate results that accompany the establishment of the nature of defects and energy characteristics of the defects of superficial structures based on metals and silicon dioxide during the process of production and during the use of semiconductor devices during some impacts. So the relevance, I believe, is quite obvious and significant. And then, what can be mentioned about the results and the provisions? The main results are new to my mind. They were obtained for the first time, and they make a contribution to the physics of condensed state. As for credibility of results, it is explained by the use of state-of-the-art equipment, helium ion microscope. So that's the equipment of scientific Park of St. Petersburg State University. And as the chairman mentioned, the results were already published in works in journals that are indexed on Web of Science and Scopus. Now I have two questions. One of them is about image 4.19, the energy structures of tantalum TO5. Here you don't give the real silicon oxide layer that has a width of several nanometers, and we can presume that it might be present here because the plate was used in atmospheric laboratory conditions before the experiment. Can we believe that the impact of a silicon oxide layer, that the influence of silicon dioxide layer is insignificant and we can neglect it? And the second question is dealing with the comparison of the studied structures. And if we consider this energy zone of the diagram of structure with two-layer dielectric, for example, silicon-silicon O2 and tantalum TO5, what differences are found here compared to diagram of structure with the absence of CO2? And overall, the conclusion is that the thesis complies with major requirements of the order and the procedure of granting academic degrees at St. Petersburg State University, and Mr. Prokofev deserves the academic degree of Candidate of Sciences in Physics and Mathematics and specialization Semiconductor Physics. That's it. Okay. Yes, thank you very much for the review. As for oxide, we try to minimize it. Before the molecular layering, we try to etch it. And it's likely that we did not manage to do that, but holding some studies, preparatory studies, we believe that it does not introduce certain significant changes into the spectra that we obtained. And as for the electron composition of the multilayered structures, so here is the picture that I wanted to show you. The major peculiarity here, there are several peculiarities here. The one thing is that we have a change of change in the fields, and if we have two-layer structure, the tantalum pentoxide pushes the field to silicon dioxide, to silicone. And another peculiarity is that in case of electroluminescence, when electrons are injected from the electrolyte, during the current passage, electrons need to overcome two potential barriers on the border of tantalum pentoxide and then silicon dioxide border. And at that, we experimentally established that such a push is easier to carry out than just to push silicon dioxide. And we see it in the leak of current. The flow of current has increased when we did it. So that's it. Yes, thank you. Are you satisfied? Yes, I am. Okay, then it's finally my turn. So my opinion is as follows. First and foremost, it was already mentioned that as for the relevance, then tantalum pentoxide, if we list all the applications, it will take 2 lines because that's not just electronics. These are catalyst sensors, optic coatings, and so on. So essentially, if we talk about optic characteristics, these luminescence studies are quite in demand. And when I wrote the review, I flicked through the literature in the set, and I just wanted to see the number of publications dedicated to tantalum pentoxide, and there were more than 1,000 works in the recent 2 years, and it demonstrates that this question is quite relevant, the topic is quite relevant, and I believe it will stay relevant for long. The second thing that I wanted to share is that tantalum pentoxide is obtained by a variety of methods, and I believe the advantage of Vladimir is that he chose molecular layering ATL method that allowed him to obtain samples, and it provides high accuracy when getting the thickness of layers and when securing the necessary composition. Because for such binary materials, stoichiometry is one of the significant parameters that influence a lot, and he really improved, updated this technology. It required a lot of efforts, and the result was quite good, which demonstrates the high qualification of the author. And the second point that I wanted to mention is that these 1,000 of works dwelled upon different characteristics of the material. But if you take luminescence, the author mentioned the bands that he discussed. Essentially, that's not a lot that was done, because as for the applications of this tantalum pentoxide, it's not used as luminophore. Therefore, that's just a kind of byproduct. And from this method, from optic method, you can get new information. And it was actually done, and electroluminescence was studied for the first time. And yet another thing is that I want to emphasize that here we have a problem in this methodology that was given for the first time, that the samples degrade too quickly when the current penetrates them. And in order to resolve the problem, in order to get credible data, I'm talking about credibility here, you needed to actually conduct a lot of works in order to resolve this degradation problem, and it was successfully resolved because the author created a new automated installation, and there are a lot of interesting ideas that can be used independently and can be checked independently on this installation. Next is that the results are very well tested and recognized. I won't dwell upon that, but I believe that, well, credibility was already mentioned, and I should also mention the fact that these results expanded the fundamental understanding of defects in these dielectrics and electronic processes, and it defines them, their scientific and practical value. And now remarks. The first group of questions I've already asked some of them after the report. The first question was about the technology. In the thesis, you give the parameters that you use to obtain stable, even layers. 200 degrees Celsius, the evaporator temperature is 70 degrees Celsius, and the speed of 4 turns per second. And what are the margins of this? The margin of variation, and how the films differed according to the parameters. Then in the thesis, you don't describe the structure of the film. Was it polycrystalline, amorphous, crystalline? Third question about the technological part. In order to obtain pentoxide, you used precursors that contained chlorine that could be included in the content of the layers as an admixture. this possibility is not described in the thesis. And it is interesting that there is significant difference of photoluminescence spectra from other results obtained during excitation. And the reason for that is not described in detail. And the third thing is that the thesis has some incorrect wordings, and also you write that elementary analysis was carried out using helium ionic microscope Orion. But all these remarks are not fundamental ones. Therefore, I believe that the thesis by Vladimir Alexandrovich complies with the requirements of the order on the procedure of granting academic degrees at St. Petersburg State University. And Mr. Prokofev deserves the academic degree of Candidate of Sciences in Physics and Mathematics and specialization Semiconductor Physics. And according to the protocol, I need to say that Articles 9 and 11 of the above-mentioned order are not violated. So please, you can answer. Yes, thank you very much for the remarks and for the comments. As for the differences of photoluminescence, I've partially answered this question, and photoluminescence has three basic peculiarities that makes it different. First is excitation. In our case, photoluminescence lacked energy for silicon dioxide to push electrons to the conductivity zone. And second is that we believe that we have different character of luminescence on silicon dioxide and tantalum pentoxide. And it's interesting that our luminescence processes are competing, and if in case of cathode electroluminescence we push high energy electrons in photoluminescence, these are, well, we can scan them on the energy. And as for the obtaining of and as for the methodology, it is as follows. Initially, when we started the experiment, we did not know the range of temperatures, and we tested them in the broad band of temperature. And essentially, it turned out that we had to change the substrate, the reagent temperature, and rotation speed, and it turns out that lower than 60 degrees Celsius, the reaction does not happen. We just charge the plate, and that's it. And at temperatures higher than 80 degrees, we see that on the surface there are such, tablets formed, and there is and the pressure is becoming too strong, and molecular layering cycle is destroyed. And as for the substrate temperature, it turned out that 180 degrees centigrade does not give rise to the reaction, and before that we take empty plate, and starting with 200 degrees and higher up until 240 degrees, there's no difference across the samples. Therefore, we chose the temperature of the reagent with the temperature of the substrate. And as for rotation speed, we tried to get the maximum speed at which we can have one ATL cycle, and we chose this speed of 4 cycles a second. And the question about chlorine. Yes, elementary analysis shows that chlorine was the precursor, and it was contained in the films. And strictly showing that chlorine does not impact the study is something that I can't do, but in literature there are references that show that for dielectrics, chlorine impurities are not active. And as for silicon nitride, there is a work that describes that it does not influence. Therefore, similarly to other dielectrics, we can presume that it does not influence, but I can't prove it quickly. And as for the structure, yes, for the structure, we carried out diffraction experiments, and they showed that we have they're not crystalline, but there are admixtures of crystalline structures as well. Thank you. So that's it for the speeches of the members of the board. We don't have any guests, but we got a question from the email from Vnim. Did you study isotopic content of the substrate? And I studied some samples during the study of the content impact on luminescence. Well, we obtained luminescence spectra. Therefore, we believe, for the substrate, therefore we believe that this spectrum has low intensity, and for silicon dioxide, it is found in the different area. Therefore, we believe that substrate does not influence. No. They were talking about isotopic content of the substrate and the impact of content. I believe that's the chemical content that they are asking about. Well, isotope content was not tested, and the chemical content was tested on the installations of the resource center. And how? X-ray structural analysis, X-ray spectral analysis, okay. No other questions? Okay. So now I'd like to give the floor to Alexander Petrovich. Thank you, Oleg. So you gave the floor to each and everyone. Oh, what can I say about Vladimir? Only the best things. If we talk about his work, I can give you just an example that he took our hardware, MTR2, developed installation that was fine-tuned, and currently we have a spectrometer that is no different from the best Japanese samples. So the time is 1 second with full analysis, this control time, and we re-equipped it with a light diode at 260 nanometers, so we can see photoluminescence as well. And I would like to thank Vladimir for taking this work until the end. He was patient. We had reasons for the delay of the defense, and part of them are quite objective. But still, he did his best. He struggled a lot, and it was rather hard to combine his thesis work with everyday work that he has. But still, he managed to do that. And currently, I believe that he is a well-established expert in the field, and he can not just achieve the goals that were set, but he can independently set these goals for himself and for his colleagues. And I believe that Vladimir's work fully meets the requirements of plans for the degree, and I believe that Vladimir deserves the academic degree of the candidate of sciences. Thank you, Alexander Petrovich. Now, according to our agenda, we may give the floor to the members of the board who want to comment something. Well, unfortunately, we don't have any guests, so it turns out that the members of the board should be given the floor once again if they want to comment on something. No, okay. Therefore, we stop the discussion and we stop taking questions. And before we draw the conclusion, I would like to ask all the members of the board and the candidates for the degree if there are any remarks or questions about the procedure. Maybe the questions associated with the organization of remote defense. So I need to ask each of you. You can just say no if there are none. No? Okay, Denis, no? No, no, no. Okay, everything is okay. Now I would like to give the floor to Vladimir for the finalizing remarks. First of all, I would like to thank the members of the board, the chairman. Thank you very much for your reviews. I hope that they will help me in my future work. I would like to thank my academic supervisor, Alexander Petrovich, for his consultations and for the lessons. And I would like to thank colleagues and friends, Andrei Gonchala and Yuri Petrov. I would like to thank my wife and my son for their patience and support. And I would like to thank the university colleagues who helped to organize it, including Natalia Karpova. Thank you very much for that. Thank you, everyone. Thank you. So you can take a seat. Now the question to the members of the board: do we need to make a break in order to discuss something in a closed manner? Or can we vote straight away? Yes, we can vote straight away. Okay, if we start the poll, it should be open, and I need to ask every one of you. So, Denise, do you vote for the award of the academic degree? Yes, I do. Maria, yes, I vote for the award of the academic degree. Yes. Yes, I also agree. Yes, and I also agree with the award of the academic degree. And certainly I vote for the award of the academic degree to Vladimir. So, based on our vote, our board decides to so I need to read this phrase. Okay. Well, thus, all the members of the board voted for the award of the academic degree to Mr. Prokofev. Therefore, we decide to award the academic degree to Vladimir Prokofev, and I would like to congratulate you with that. Thank you, everyone. Thank you, all the members of the board. And I thereby close our session, and I would like to thank everyone for participation, and please turn